Yes, yes.
All right, here we go. So, real quick disclaimer. I try really hard to make this class relevant to your lives. Static electricity has a tendency to be really mathy and really theoretical, especially this lesson. And so my presentation, if you try to take this to college, you're going to be like, what were they taught? There's a whole math side of things to this that I'm not going to touch. What I'm focusing on is what really matters, and that is electrons. Okay? There's a whole math side of things that says you can look at positive charges and negative charges and do a lot of math, and it's robust, but you kind of get lost in the weeds of like, why do I need this for anything? So kind of putting all that away and let you experience that in the future and give you some conceptual understanding of what this is and how it plays a part in your life. Okay? So, tell your neighbor what you think. Correct answer is A. So here's my analogy. Pretend these are connected by compression springs. Which arrangement is there more energy stored in the springs? A. Crunched in there more. Good with that? Electrons are equally crowded. Tell your neighbor what you think.
Nope.
What do you say? Correct answer is B. Here's why. So the springs between them are equally compressed. But there are more springs in this than in this one. So you're adding up all the energies together. This collection of springs has more total energy than this collection of springs. Simply because there's more springs here than there are here. Okay with that? Same scenario, which one has a higher electric potential? Tell your neighbor.
So we're gonna move it back to range.
What do you say? C is the correct answer. Okay. So here is what is electric potential? This is technically how much energy there is per charge. This is what a textbook would say, per coulomb. I'm gonna boil that down conceptually, is how much energy there is per electron. And the way that that's gonna be depicted is how crowded the electrons are. Okay. The more crowded the electrons are, the higher how much energy per electron there is. You okay with that? Okay, so technically, this would be a better description conceptually of electric potential, but I'm not gonna camp here. This would be helpful for college. You know the relationship between how electric field is the promise of an electric force? Electric potential is the promise of electric potential energy. It has that same relationship. So that explanation would hold up in college. This explanation would not. But it helps us understand why things do the way they do. Good? Okay.
Is it possible in like a certain field that an electron or like two electrons would be at a different distance than other two electrons in that same field? Like if you had like in that example, can it be possible that they're spaced unequally?
Oh, great question.
What would happen if they're spaced unequally?
Beautiful question.
Yes.
Okay, so for my lesson, for this model to work, we're just using spheres.
Okay.
And we're pretending like in a sphere it would equally distribute. On something that isn't spherical, it's not a equal distribution in my analogy for all the parts. So for our conversation, everything's a sphere. Great question. Tell your neighbor the answer to this question. Correct answer is what? How are we doing with A? Why?
More dense.
More densely packed. The electrons are more crowded. Like in here, and this is like. Good. Okay, has a higher electric potential. Is it possible for object 4 to have more electric potential energy than object 3? Have a conversation. Is it possible?
Or like state it's connected
It's just whatever. Whichever has more dense, higher density of electrons will have higher density.
So electric potential energy is electrons.
Correct answer is sure, possible. Okay. Why? Because yes, the spring here is not as tightly compressed as like that's like crazy. Like, oh my goodness, there's definitely more energy in that one spring than there is in this one spring. But at some point, if you have way more springs with less energy, you add them up. At some point, you can get more energy total than you can here. You all right with that? That's kind of what I was going for. Okay. All right. Variable for electric potential, capital V. Electric potential difference, capital delta V. Or delta capital V. The equation for electric potential difference is the absolute value of electric potential 1 and electric potential 2. So, question for you is, what would cause the electric potential difference to increase? What would make that bigger? Okay. Hopefully you said a bigger contrast in the electric potentials. Good with that? Bigger the difference. Using the word to define itself. Bigger contrast between these two. Okay. Bigger difference in crowdedness. Okay? So, have a conversation. comparison between 4 and 1, between 4 and 2, and 4 and 3. Which one has a bigger difference?
Because they all the same. But it's not the same. No, they're saying 1, 2, and 3 are all the same. Yeah. So they don't need the same distance.
Neighbor, what you say is.
That's the
Correct answer is C.
Yeah, there we go.
Okay. Here, it's definitely more crowded here than in here, but like the comparison of crowdedness, there's a whole lot more room here than there is here. Okay, with that, they're less crowded over here. So like the comparison of crowdedness, there's a bigger difference in crowdedness. Okay, with that. Tell your neighbor. What do you say? Correct answer is D. Dangerous dinosaurs. You right with that? Equally crowded. Okay? All right, so trying to make some connections with life. I don't care about dots on a board. Like, you ever heard of voltage? That is the exact same thing as electric potential difference. Electric potential difference and voltage are the same thing. Okay? So, another equation other than just the difference between electric potential is the amount of energy transferred over how much charge is transferred. Okay, here's another way to describe electric potential difference. That. Okay. Now, here's where it becomes real life. So your voltage, your electric potential difference, determines how motivated the electrons are to transfer. How motivated the electrons are to transfer, okay? How big of a jump they can make to get to a less crowded environment. Okay. Electric potential energy that's transferred, this determines how powerful or painful the shock is. At the end of the day, this is what determines if you live or die. That's kind of what we care about. Like, hey, that would be good to know, right? So, what would cause the amount of energy transferred to increase? Like, what would make it fatal? So we use this equation. I bring charge transferred over here to equal potential energy. So that would be, you either have a very high, or you have a high voltage and you have a lot of charge transferred. That's going to cause the amount of potential energy to be big. So if you have high voltage and there's a lot of charge transferred, a lot of electrons being transferred, that's death. Okay? Kind of want to stay away from that. Good. Tell your neighbor. Correct answer is correct answer is C. There's a greater electric potential difference between these two. Therefore, there's more motivation. These guys are like, man, that looks way better. But these guys are like, what? Look at all that space. This way more motivated than this. They are motivated, but this is motivated more. You all right with that? Have a conversation.
Not really. It's so confusing. Like I understand it, like if I got a problem, like I don't think I can solve it. Like
Good.
yeah.
What do you say? Correct answer is bountiful buffaloes. Okay, so they're gonna go until they're equally crowded. Like, oh, if they like all went over, they'll be like, what? Whoa, it's better over there. So they're gonna go until they're equally crowded. Okay with that? Have a conversation. I predict this will be a good one. Find someone.
See?
You said we should keep at it. Let's hear it.
What's your latest FBI and what was right now, we're just something.
Like, we literally
Think
did
of
this.
like what's in a s'more.
What do you say? Gotta vote for C. Everybody agree with C? I'm gonna venture the answer is B. Here is why. They are equally motivated. I'll give you that. Okay? They have the same voltage. Same comparison of crowdedness. However, check this out. Let's say one electron jumps. You get 4 electrons. This is symbolic. Okay? Now, we're about equally crowded, like, we reduce the number in here and increase the number in here. Now we're like equally crowded. Like, okay. Versus here, if I put 4 electrons, there's still more room to spread out. You okay with that? So this one can handle more than 4 electrons. So there's going to be more electrons jumping, providing a greater amount of energy transfer. Okay with that? Yeah. All right, so who cares about dots? That's a question. Okay. Does anybody know what the voltage of an outlet is? 110, 120, depending on who you talk to. Okay? 120. High voltage power lines. Caution, warning, high voltage. You've seen signs, and they got a number 480. I've seen them from 2,000 to 20,000. Like those big electric playgrounds, like with all the barbed wire and like huge fences, those like the big jungle gyms that are like forbidden. You know what I'm talking about. Maybe I'm one of the few that are like, that looks tempting. 20,000. When you charge an antigraph generator, that is somewhere in the neighborhood of hundreds of thousands of volts. Hundreds of thousands of volts. Compared to an outlet. Like, you don't want to stick your tongue in an outlet. That would be bad, right? Like, why are we having, like, I put my hand on that yesterday. Like, what? Okay, so we need to now understand what voltage is and what it is not. That makes sense? Like, you've heard of this word voltage before, but many of you, most of us, wouldn't have just be able to like put it into words. That's what the goal of today is. Okay. So I'm going to do some experiments. If I take a cord and I plug it into an outlet, am I, as long as I'm touching, like holding on to this part and not the metal, am I safe?
Should be,
Yeah. I mean, we do it every time we plug something in, right? Yes? Even this part, like I'm okay so long as the cord isn't frayed or like cut or something, okay? So what I'm going to do is I'm going to plug this in to the Van der Graaf generator. Okay? And
I wish.
I want to see if I am going to be protected from being shocked. See that? Was I being protected from being shocked?
yeah.
Did you see sparks onto my hand? That was me being shocked.
No.
It was.
Yes?
It
Oh, my
was.
bad.
I was being shocked. I was not being protected from being shocked. I was being shocked. Okay? Did you see the flashes? That was to my hand. As I was holding it like this, it was going through the insulation. Okay? So, the high voltage, what that says is these electrons were so crowded and they were motivated enough, they look at this insulation and just scoff at it. Like, are you kidding me? Like, pff, I'm through that. You are not safe from being shocked. I'm going to go to better lands through this. Like, that can't stop me. I'm that motivated. You okay with that? Okay, super motivated. Now, if I take this, I'm going to take some steel wool. Okay. And I'm going to shock it with the Van der Graaf generator. Safety first, kids. Okay. Ready? Nothing. Do not do this at home. What I'm going to do is I'm going to plug this into an outlet. Okay? And I'm going to do the same experiment with the steel wool. Okay. Don't look directly at this. Look at my face. Okay, ready? Look at my face. 3, 2, 1. Okay? Destroyed. Okay? 120 volts. 100,000 volts. What is the deal? Alright, so we had 120 volts between 2,000 and 20,000 volts, and this is like hundreds of thousands to a million. In somewhere in there. Okay? That's the voltage. Was I safe from being shocked? No, it shocked me. Because the electrons were very motivated. Oh, just kidding. Yes. That goes on the next question. Was I from an outlet? Yes, safe. There is only 120 volts. Okay? Not that motivated. Okay, in comparison. Am I safe? No, I was being shocked because very high voltage. Whoop. Electrons, very crowded and very motivated. You okay with that? So, why didn't that destroy me? Okay. The voltage is really high, but the amount charge transferred was very low. Meaning there wasn't that much energy transferred. Okay? Amount of electrons on the Van de Graaff generator was crowded but very limited. Okay, they had a small number of electrons. So the amount transferred was really small, so the amount of energy, even though there was had a lot of energy per electron, there weren't that many electrons on there to begin with. Versus in an outlet, the voltage is smaller, but the amount charged transferred was huge. Okay, so there were an endless supply of electrons transferring. causing a lot of energy to be transferred. You have that, like, think of how many electrons are in an outlet. It's like, you might not have a lot of energy per electron, but there's just a lot of it. Here's my analogy on a global economic scale. Kuwait is a oil-rich company. Individuals in there, like everybody in there is super rich. They have a car per day of the week. But on a global scale, Kuwait's so small that they don't do much. China, the amount of money per person, they're pretty poor, energy per person. But on a global scale, because there's so many of them, they are a big player on the global economy. Does that make sense? So like, the Van der Graaf generator is Kuwait. Very motivated, but there's not many of them. China's like the outlet. There's not much money per person, but collectively, they're a big player in the global economy. Get to that? Okay. Here's the forecast the rest of the week. I have a worksheet due tomorrow. I'm going to give you a review worksheet that'll be due on Monday. Review test on Tuesday. Okay.